doing their
we have somewhere to click the button, so I mean not listen, this is somebody else.
yeah, so you should be able to see, doing their
we have somewhere to click the button, so
okay,
not listen, this is somebody else.
yeah, so you should be able to see, doing their
we have somewhere to click the button, so
okay,
not listen, this is somebody else.
yeah, so you should be able to see, doing their
we have somewhere to click the button, so
okay,
not listen, this is somebody else.
yeah, so you should be able to see, doing their
everyone, I'm getting quite a bit of feedback. We are live now on Event Mobi. The stream is started. If any of the presenters have the Event Mobi stream going, please mute the speakers from that, and we'll get started in a minute. I believe we're still waiting for our first presenter to join.
Yep. Okay.
Yeah, the echo seems to be recovered now, I think. Yeah, still waiting for Tom to join. Kaley, did we want to maybe do opening remarks while we wait for Tom?
Yes, I think that's a good idea. I'm going to introduce myself. You're going to introduce yourself, and then you're going to do the stuff that's on the list.
Okay.
Okay. So welcome everyone. I'm Kaley Walker from the University of Toronto. Thank you very much for coming to our session. I'm going to hand over to my colleague Alec Casey for some more opening remarks.
Great, thanks, Kaley. My name's Alec Casey. I'm a physical scientist at Environment and Climate Change Canada in the Satellite Earth Observation section of the Meteorological Service of Canada. So welcome to session 6010, Satellite Earth Observation, a unique view of our planet and a critical need for Canada. This is a multi-part session. We have 4 parts. So we have 3 sessions in a row today, all in the same Zoom room, which matters for Kaley and I. And we have another session tomorrow. So bonjour à tous et bienvenue à la session 6010, l'observation de la Terre par satellite, une vue unique de notre planète et un besoin critique pour le Canada, the première partie aujourd'hui. Before we get started, I'd like to begin by acknowledging the Indigenous peoples of all the lands that we're on today, gathered from wide and far across Canada. While we meet on a virtual platform, I encourage everyone to take a minute to acknowledge the importance of the lands which we each call home. Today, I'm joining from Ottawa on the unceded and unsurrendered territory of the Anishinaabe Algonquin Nation, whose presence here reaches back to time immemorial. I encourage everyone to learn more about the lands on which they are based and the past and the present of the Indigenous peoples that live there. So today we have 5 speakers lined up, and we have 15 minutes for each speaker. Encourage the speakers to stick to time. So we're asking you to present. We'll give you 2-minute warning at 10 minutes. Try to keep your presentations to 12 minutes, and then we'll have time for 3 minutes of question and answer. We do have a bit of room in our schedule because we have fewer speakers, but to try to keep in line with other sessions, if we can stick to time, let's try to stick to time. And I've lost my Word document and I don't know what else I'm supposed to say, but I think that is mostly it. Presenters, please keep yourselves muted when you are not presenting, and we'd appreciate if you can stay for the full session in case there's time for more discussion at the end. And with that, I believe we're still waiting for our first presenter. I don't see Tom on Zoom yet. So Kaley, not sure if we want to switch up the order slightly or try to stick to the existing order and maybe put Tom at the end, given we do have extra time.
At this point, I think we were told we were supposed to stick to the time as best we could. So how about we play an interesting game? For those who are on the event Mobi, can we have some highs and who's here and where you're coming in from? I hope everyone's allowed to.
I do have the chat. Oh, I do have the Event Mobi app on my second screen. So watching there, if anyone wants to introduce themselves, say hi and where they're joining from, and we'll get started shortly, either when Tom shows up or we'll get started at 12:30 for Paul's talk if we miss Tom. And we can add Tom in at the end of the session because we do have some time following Doug's talk if need be.
Great. Thanks for joining us from Edmonton, Rob. Hey, Ray.
And this is a good test for us to see how the chat works, and we do need to keep two windows open. So I will do my best, Kaley, to watch the chat and questions in Event Mobi during the discussion.
Great.
And yes, I think everyone, Peter, I think everyone had some going through their emails trying to find the right link for the right session, but glad that you've made it. Great to see a crowd from all across the country. Bonjour, Sandrine. Hi, Yi, Jipeng, Emily, Annie. Great to see people from all over the country. Again, if you've just joined, I see our numbers going up slowly. If you've just joined, we are waiting for our first presenter to join, and we're going to try to stick to the schedule. So we will get started at the latest in 8 minutes from now when it's Paul's turn. And we do have some time at the end of our session to, if Tom does get into the Zoom, to have him go at the end of this session. So please appreciate your patience and hang on for a couple more minutes till we get started in this session.
Okay, I think I'm going to come up with another question, which would be, how do you use satellite remote sensing in your work? Are you looking at the land? Are you looking at the ice? Are you looking at the air as we're talking about right now?
A little bit quiet in the chat so far, so maybe I'll get started. So I'm Alec from Environment and Climate Change Canada. My background is in remote sensing of Arctic sea ice, but since joining the Meteorological Service of Canada 5 years ago, have been focused more and more on atmospheric remote sensing, and am now part of the Atmospheric Observing Mission team, which we will hear about in part 3 later today of this session, in the final session today. So interested in surface observations and atmospheric observations to support numerical weather and environmental prediction and forecasting activities. So encourage everyone to speak up in the chat. I see we have some answers coming in. So we have some operational meteorologists, some folks working on air quality, clouds, radiation, and their interactions. So a good mix. Sounds like mostly atmospheric focused, which makes sense for this session, given the talks that we have lined up. I believe our part 4 session tomorrow is a bit more focused on surface observations, with our parts 1 and 3 primarily on atmospheric remote sensing. So thanks everyone for putting in your feedback into the chat.
Ah, nice. A good collection of different ways to look at things. Okay. One more thing I was going to ask while we're waiting, could we go around the presenters and just have them give a brief introduction in the 4 minutes we've got to themselves?
To themselves or of themselves?
Of themselves.
Okay. I'm Doug Degenstein, Professor of Physics and Engineering Physics, University of Saskatchewan. I've been involved in atmospheric remote sensing from satellite platforms for well over 25 years, and I will be doing the OSIRIS presentation later today.
And as I introduce myself, I'm Kaley Walker, Professor of Physics, University of Toronto. I'm the Deputy Mission Scientist for SCISAT, or the Atmospheric Chemistry Experiment, and I'll be talking about ACE-FTS science and validation results. Over to Paul.
Hi, everyone. I'm Paul. Nothing quite so fancy as these first two. I'm a research associate at the University of Toronto, working primarily with the MOPIT instrument on NASA's Terra satellite and the MAESTRO instrument on the Canadian CISAT satellite, doing operations and data validation respectively. On top of all this, I also do a little bit of work with ACE-FTS, also on the Canadian CISAT satellite.
And Jason, please go ahead.
Yeah, I'm Jason. I'm a research associate at the University of Toronto. I have been in this group for more than 20 years. I first joined the group from Jim Drummond, and I work on the MOPIT operation, then MAESTRO operation, and in recent years, I'm working on the ACE-FTS validation.
Jason, do you have the Event Mobi app open?
Yes.
I think you might be helping with the echo.
I should close it.
Or you can, yeah, close it's probably the easiest.
Yeah.
Or mute it. Great.
So it seems like the act from me.
Okay, we've got 2 minutes till 12:30. Maybe one more question interested in knowing. I recognize quite a few names on the chat from Environment and Climate Change Canada, a few people that I know from academia. Wondering if there are any students listening in to our session today. So if there are any students, let us know, or feel free to let us know where you are in your career, whether you're industry, government, academia, as well. And in 2 minutes, 1 minute, we'll be starting with Paul's talk. So interested in knowing a little more about our audience, and then we'll get started. Okay, Kaley, I see 12:30 on my phone. So I'm going to stop sharing and we'll pass it over to you, Paul, to present to us on validation of version 4 MAESTRO ozone and NO2 measurements. So Paul, please share your screen and we'll be quiet and enjoy your presentation. Thanks.
Yep, let me just bring this up. And hopefully you all can see this.
Yes, it's full screen.
Yes.
Thanks.
Okay, perfect. Hi, everyone. Today I'm going to be talking about validation of the version 4.5 MAESTRO ozone and NO2 measurements. As a quick note for the discrepancy, I know the talk title on the event Mobi says version 4. Well, we've had a few iterations on the version, and we're now up to the brand new version 4.5. So the instrument that I'm going to be primarily talking about today is the MAESTRO instrument, the measurement of aerosol extinction in the stratosphere and troposphere retrieved by occultation. So Tom, who was going to be originally presenting just before me, is going to go really in depth with the instrument in his talk, but you'll have to suffice with my brief overview here. And what MAESTRO is it's a pair of UV vis near-infrared grading spectrometers that employ the solar occultation technique to make measurements. So MAESTRO itself records spectra in the 285 to 1030 nanometer region with 122 nanometer resolution and with a vertical field of view of about 1.2 kilometer on the limb. So that's above the Earth with a 1 to 2 kilometer effective vertical resolution. So this MAESTRO instrument is one of two main instruments on the Canadian SCISAT satellite, along with ACE-FTS. In the top picture, you see SCISAT, and in the lower picture, you see the MAESTRO instrument from testing. Now, one thing that's relevant to note is for the two spectrometers, the UV and the visible, after 2015, there's been no light with wavelength shorter than about 500 nanometers that has been transmitted through the instrument. And so this caused our UV measurements, or the measurements recorded from the UV spectrometer, to no longer be functional. As of late 2023, however, there's been a recovery to about 20% of the initial intensity for the UV channel. However, we're still not sure why this has been the case, and this is still undergoing investigation. And so for the UV measurements, we have cutoffs earlier in the mission. Okay, so the actual version 4.5 retrieval. So the trace gas retrieval for MAESTRO is based on a two-step approach, where a differential optical absorption spectroscopy at DOAS technique is used to yield line-of-sight column densities, and then a Toomey-Tikhonov algorithm is used to invert these to yield volume mixing ratio profiles. This is done on a retrieval grid spanning from 5 to 80 kilometers. And as part of the retrieval, this is extended past 80 kilometers up to 100 kilometers. However, the data there are not to be used for any real and scientific purposes. They're just extrapolations. The inversion for version 4.5 uses temperature and pressure information as input, which comes from ACE-FTS version 4.1 and 4.2. So as I said, the two instruments are co-located on the Canadian SCISAT satellite, and they make measurements along the same line of sight. ACE-FTS measures temperature and pressure directly, and so these are used for the MAESTRO retrieval. Currently, we have three main viable products from MAESTRO. There's a visible ozone, a UV ozone, and an NO2 product. The UV ozone is viable up until December 2009, the NO2 until July 2009. As I said, with some recovery being observed, these might be improved and we might actually have a product extending forward from late last year. However, for now, we're going to focus on just using these as the cutoff dates for discussion. So first step in doing a lot of this validation is getting a set of instruments for comparison. And I've chosen a set of 11 different comparison instruments. And for one of them, I have two versions for use. We have ACE-FTS, and that's the one with two versions. There's the version 4.1 and 4.2, which is what's used for the MAESTRO pressure and temperature, as well as the version 5.2, which is the current operational version. Then we also have OSIRIS, Odin SMR, GOMOS, MIPAS, SCIMAC, or MLS, OMPS, SAGE 2, SAGE 3 on the Meteor satellite, and SAGE 3 on the ISS. Each of these covers a different period of time and has a different observation method. However, we tend to cover solar occultation, limb scatter, and limb emission as the principal ones used. And just as a handy chart, from this we see the time period of operation for each of these instruments, including MAESTRO, and whether they measure both ozone or just ozone and NO2. I should state that for what's shown here, both OMPS and SAGE 3 ISS do have an NO2 product. However, these satellites were only, or sorry, these instruments have only been in operation since after the cutoff date for the MAESTRO UV NO2 product, and so they're not used for comparison. As you can see from these two handy cutoff lines. So for the actual comparison methodology, comparison profiles from the other instruments were linearly interpolated onto a uniform 1 kilometer grid spanning from 0 to 100 kilometers to match the MAESTRO retrieval grid. Then two coincidence criteria were employed, a temporal criteria requiring measurements to be made within 8 hours of each other, and a spatial criteria requiring that the measurements are made within 1,000 kilometers. For NO2, an extra consideration had to be made for the strong diurnal cycle observed in that species. And in order to do diurnal scaling, to scale it so that measurements were made at approximately the same time of day, we used a set of climatological monthly mean, multi-year mean, zonal mean scaling factors produced by Strode et al. And we really focus here on 3 different comparison metrics. I'm sure you've all used them numerous times before in various works, just the absolute difference, relative difference, and the Pearson correlation coefficient. We just have the formula and the definitions here. Again, very much in line with what one might see in any sort of validation work. Now, let's delve into some of these actual comparisons. And for this, I've separated the comparisons into sunrise and sunset, since there is a slight asymmetry in how these measurements are made, and it's a noted effect that if you combine them, there's a bit of a biasing. So we've separated into sunrise on the left and sunset on the right. And we see generally pretty good agreement. In the black dashed line, it's the mean of the agreement. And then you see in the color coordinated sections, each of the 12 comparison data sets. The dotted and dashed lines are the MAESTRO measurements coincident with those data sets, and the solid lines are the comparison data sets with a coincident MAESTRO measurement. So these are just the mean profiles of the two, and we see generally very similar shape for everything except for SAGE 3 on the Meteor, which above about 55 kilometers, we see this oscillatory increase. Now, how do these directly compare? Using the same color schemes from the previous slide, we see generally sub 1 ppmv difference between the MAESTRO and the comparison instruments, very small at low altitudes, from about 0 to 20 kilometers, where maybe 0.1 ppmv for the most part, except for at the lower bounds of the altitude scale. From about 20 to 50, we're about 0.4 ppmv on average, which is overall pretty good, especially when you turn to the relative difference, where we see great agreement in the stratosphere, but even those small disagreements in the troposphere result in very large differences when you move over to relative differences due to the magnitude of the comparison values there. But in general, we see pretty good agreement within a couple percent for the most part. And for profile correlation, we see similarly very positive results. From about 15 kilometers to about 40, we see really high correlation of about above about 0.6, with the correlation peaking around 0.9 for the ACE-FTS comparisons, which is expected since they share line of sight, with this peak around 30 kilometers. So all in all, very good results for the most part. Turning then to the UV product, we see that there's also pretty good agreement from between the MAESTRO visible and the UV. Taking a look going left to right, we have the mean profiles, mean coincident profiles, of course, between the two. We have the absolute difference, the relative difference, and the correlation. And we see very small differences from about 5 to 50 kilometers in both in the absolute difference, and small differences of about 2 to 3% from about 20 to 40, 45 kilometers. So again, these two products are found to be in pretty good agreement with each other. And then turning to the third product, the NO2, we see, unfortunately, not quite as good of a comparison, with the profiles wildly varying as compared to what we saw with the fairly tight envelope for the ozone. However, we still have pretty good correlation from about 15 up to about 35, 40 kilometers. And the relative differences and absolute differences are within 20 odd percent from about 15 to 35 kilometers, which for those of you who've worked with NO2 before is broadly an acceptable range. It's not perfect, however, we see that a lot of this difference, even between the different data sets, is manifested. And so just overall in summary, the version 4 MAESTRO ozone and NO2 products are found to have pretty good agreement with each other, particularly in the stratosphere. For the visible ozone, there's a small high bias about with differences between about 2.3 and 8.2%, and high correlation above 0.7 between about 15 and 40 kilometers. For UV ozone, there's just the small high bias of about 2.9 to 11.9%, with high correlation between a slightly narrow range. And for NO2, there's a low bias with the difference between 8.5 and 43.4%, and a high correlation between about 15 and 40 kilometers. And this is just another slide showing those exact same comparisons with a little bit more detail. Thank you all.
Great. Thanks very much, Paul. Are there questions from the audience?
I don't see anything in the Event Mobi chat yet. So for all the audience listening online through Event Mobi, if you do have questions, please put them into the chat. Let me just double check the Q&A tab. I don't see anything there yet. I have a quick question for you, Paul, although you may not have an answer. I was curious in the introduction, you talked about the recovery of shorter wavelengths on the instruments in 2023, that you're not sure what has happened. Can you give us any insights, or are you involved at all in trying to understand what's happened there? Interested if you have any information, just really curious. So and totally okay if that's a
yeah, so I am a bit involved in trying to identify what changes, and we kind of have no clue at this idea. There's a few theories about different chemical species that may have off-gassed over the years, some bonding agents possibly, but I don't really have anything concrete I can tell you right now. We're hoping to get to the bottom of it at some point, and hopefully we might even get another paper out of it at some point, but we're just happy that the current version 4.5 MAESTRO seems to be showing pretty good agreement throughout the stratosphere. It's another 20+ year data set for people to use, and these comparisons are generally pretty good. We're hoping people might actually start picking up this data set and using it for a wide variety of purposes. I know it's been a bit of a touch and go data set over time, and we're happy to see this change.
Thanks, Paul. I'm just going to do another check in the chat and the Q&A, and I don't see anything yet. And we're right on time at 12:45. So I'll hand it off next. Thanks, Paul. I'll hand it off next to Kaley for presentation on the Canadian Atmospheric Chemistry Experiment, 20 years of validation and science results. Go ahead, Kaley.
Thanks very much, Alec. Okay, so I'm going to continue our theme on talking about ACE. I'm going to focus a bit more on the ACE-FTS instrument, and I want to acknowledge all of the co-authors at the University of Toronto who've contributed to the work that I'm going to present. So moving forward. So just to give a sort of a bigger scale of what we do with the atmospheric chemistry experiment, it's on SCISAT, and really it had a goal of producing profiles of trace gas species, cloud and aerosol extinction, temperature and pressure, with three main areas that it wanted to focus on. Looking at the distribution of ozone in the upper troposphere and stratosphere with a focus on the high latitudes in the Arctic, things that were important to Canada when it was proposed back in the late 90s, so about 10 years after the Montreal Protocol was signed, looking at the effects of biomass burning in the troposphere, and also looking at the relationship between chemistry and climate, which is something that we've really moved into in the 20 years of our operations. So this August, we will hit 22 years in orbit, complete 21 years, heading into our 22nd year in orbit. And as Paul mentioned, the SCISAT is that cute little satellite in the picture there. It's about 1 meter in diameter and 1 meter tall. So next, yes, I have control of my slides. So I'm talking about the ACE-FTS. This is the larger of the two instruments on board. So the MAESTRO, which Paul just talked about, sits near this on the platform, and they share the same sun tracker. So I'm not sure if people can see my mouse, but I'll try and indicate there's a big mirror here, and then there's a little pickoff that directs some of the light into the MAESTRO. So this is a fairly high resolution for a satellite-borne instrument, 0.02 wave numbers, and it measures throughout the mid-infrared from 750 to 4400 wave numbers. And we measure a spectrum or an interferogram, which we convert into a spectrum, every 2 seconds. So that gives us on the order of about 3 kilometers of vertical resolution. When we get to the lower part of the atmosphere, that gets oversampled because of refraction, and so we can have 1.5 kilometer spacing. In terms of the mission, as I said, we're ending our 21st year in orbit, which is great because we were designed for a 2-year mission. In addition to the degradation in the MAESTRO, we have also seen a little bit of degradation in the signal-to-noise performance of the ACE-FTS. However, the requirement was 100 to 1, and we started in some places at over 450, so we've gone down to about 375. So we've got a long while to go before we are unable to use our current retrieval strategy. Our list of retrieved species now includes nearly 50 different molecules and 20 isotopologues, along with profiles of temperature and extinction. We measured the most molecules ever measured simultaneously from space, from a little Canadian satellite. Our operations began in February of 2004, and we have an orbit that puts us with most of our measurements at high latitudes, which is great when you're focusing on Arctic science and ozone depletion. We recently had a review of our mission, and we've been approved for another 2 years, so that's to March 2026. Now, the reason one does solar occultation measurements using a Fourier transform spectrometer is shown here. You can measure many species. You've got a bright light source, and you can get beautiful transmission spectra. So the colors I used here, what we originally promised to the space agency when the mission was launched, are shown in red, called our baseline species. Our newest version is in green, and we keep, as you see, between 5.2 and 4.1, 4.2, we continue to add newer and newer species. So whether you're interested in tracers, halogen-containing gases, some interesting carbon-containing species, looking at biomass burning or isotopologues, we've got lots to provide. So I'm going to talk a little bit about validation, and then I'm going to talk a little bit about what we're doing with the long-term data set from ACE-FTS. So one of the things that my group spends a lot of its time doing is looking at data quality. And so that involves doing validation comparisons, as you just heard from Paul. These are ones done by Patrick Schiess, who's the ACE validator. And these are comparisons between version 5.2 of ACE-FTS and a variety of satellite limb sensors. There's, I think, 19 of them in our list for ozone. And this is just what we do routinely to make sure that we're understanding data quality and how things are going. In the left-hand panel here are the number of coincidences. The red line is the MAESTRO. And because they're on the same platform, sharing the same sun tracker, of course, they're going to have lots of coincidences. Then we have relative difference, standard deviation of the relative difference, and the correlation coefficient. And then the average is shown in the thick black line. And in the lower level is the comparison between what we saw for 5.2, our current version, and the 4.1, 4.2. So generally, our relative differences have improved for ozone slightly. And the standard deviations and the correlations are consistent. We also produce data quality flags, which are available to users at our data depot, and I can give you the DOI for those. You're going to hear Jiansheng Zou talking a little bit about CFCs in the next talk, but also he's been doing comparisons of ACE-FTS with ozone sondes, and this is looking at the lower part of our profiles in the upper troposphere and lower stratosphere, and using ozone sondes, so balloon-borne ozone in situ devices, to look at how well our lower part of our ozone profiles look like. And so these are different latitude ranges, starting in the upper left at the high northern latitudes and going down to the high southern latitudes in the lower right. And essentially looking at the averages between these, they're of the order of within 5 to 7% globally, which is really good, and also an area that tends to be a lot harder to look at these. He's also done some time series analysis to understand the consistency and to find that there's very little drift in our measurements. We also measure a lot of chlorine-containing compounds, as I mentioned. This is work started by Felicia Colangiari and recently completed by Patrick Schiess, which was published back in March. It's looking at the first replacement for the CFCs, which is HCFC, or hydrochlorofluorocarbon 22. And these are comparisons between a balloon-borne FTIR from JPL, called the Mark IV, and ACE-FTS. And here, because these balloon profiles occur only at certain locations at certain times, we do zonal mean comparisons, where we're averaging around that latitude of that measurement for about a month on either side, so that we get sufficient measurements, because our occultation measurements are not so easy to hit one of the balloon profiles. And so these show quite good results. Typically, the bias is within 15% or better. This is work by Laura Saunders looking at SF6. And our interest in looking at this is because you can use it to derive the stratospheric age of air, or the length of time that an air parcel has been in the stratosphere since it left the troposphere. And SF6 is great for this because it has a steadily linearly increasing concentration, and it has no sinks in the lower part of the atmosphere. You do need to account, however, for sinks in the mesosphere. So these are comparisons where she's broken things up by northern and southern hemisphere in the two rows, and then the tropics, the extratropics, and the polar vortex to look at different regions. And she's moved back a couple of different versions because it turns out that for the comparisons that we were looking at with MIPAS, another limb sounding instrument, and balloons, that the earlier version 3.5, 3.6 of ACE-FTS tended to be in better agreement. So the dashed lines are those compared to MIPAS, which operated between 2002 and 2012, and we're focusing on the overlap period between 2005 and 2012. and then comparing the longer term measurement averages in the solid lines from two different versions of ACE-FTS, and that you can see the increase in the amount of SF6 in the atmosphere when we ended only in 2012 versus 2020. So we have good understanding of our measurements through these kinds of comparisons, which gives us good confidence in that derived age of error. Alec, how am I doing for time?
You are just at 10 minutes, so 2 more minutes.
Okay, perfect. Thank you. So the last thing I wanted to talk about are HFCs. So I told you about HCFC 22, which was the main replacement. It's since been banned, and HFCs were the replacement proposed for these. The challenge that we have with these is that they're great for ozone because they don't contain chlorine or bromine, but they're awful for climate because they're significant greenhouse gases, and they're typically with global warming potentials of thousands of times more powerful than CO2. And the Montreal Protocol was expanded in October 2016 with the Kigali Amendment to include the phase out of hydrofluorocarbons. So it expanded the mandate of the Montreal Protocol beyond ozone to climate. And this is pretty exciting for an international agreement that's been in place for 37 years this September. And ACE-FTS was the first to measure HFCs from space. It's currently the only satellite measuring vertically resolved profiles of HFCs. And I show you our long list of the different fluorinated and chlorinated gases, or at least the anthropogenic ones that we do measure. So one of the neat things that we're able to do is to look at the time series of these. So this is a global view, so averaging globally and looking at a comparison in blue between ACE-FTS and a surface measurement from NOAA Global Monitoring Laboratory in red. And you can see that there's these noted X's or O's, those are the breakpoints, where the rate of increase actually has changed, and in these cases has increased as there's more and more being put into the atmosphere. This has been done for HFC 32, which is a substituted methane compound, and also for HFC 134A, which is tetrafluoroethane. This one has a global warming potential of over 1400, which is so for any kilogram of this compound, its warming potential is 1400 times that of CO2. Now, in this case, we don't see any significant breakpoint in our analysis, and there is an offset in what we see in the atmosphere, higher in the atmosphere at 15 to 20 kilometers from ACE versus that which we see from the surface measurements. So I hope I've convinced you that ACE continues to produce excellent data in its 21st year of measurements. There's where you can get our data from and our data quality flags. We've got some really cool validation that we're doing, but also using our long time series to make interesting results. So I thank those who fund the work, this in particular, CSA and NSERC. I thank the mission scientist, Peter Bernath, our project scientist, Chris Boone, and the rest of the team at the CISAT Science Operations Center, and my colleagues on the MIPAS team, Gabrielle Stiller, Mark IV team, Jeff Toon, and those on the HATS team who make their data available. So thanks very much, and I'm happy to take any questions.
Wonderful, thanks, Kaley. I'll just take a quick look in Event Mobi, and everyone, again, please. Oh, I see there is a question in the Q&A. But I think this may have been for Paul. This is about the CO2 profiles, and Kaley or Paul, feel free to answer. One of your slides said that, because I don't remember if that was whose presentation it was from. One of your slides said ACE-FTS CO2 profiles span 5 to 18 kilometers altitude and greater than 60 kilometers. Can you please remind me of the reason for the gap in altitude coverage, and are there plans in the future to retrieve CO2 in that altitude region to bridge the gap?
Okay, so the reason that there's a gap between them is that the lower altitude CO2 measurements are done. two steps back, sorry, little jet lagged. CO2 we use to retrieve temperature, and if we're going to, and so we sort of sacrifice the CO2 measurement if we want the temperature. If we know what the altitude is, and we can get that in the lower part of the atmosphere from the N2 continuum, that allows us to retrieve CO2. We're not sacrificing it. In the in-between part, we don't have really good knowledge of where we're pointing, so we need to use it to get the altitude and the temperature. And then at higher altitudes, we can substitute in information from the satellite pointing, which allows us again to know where we're pointing, so that altitude information, so we can get CO2 and temperature separately. So I hope that answers the question, and I'm happy to take offline or email questions. So thanks very much.
Thanks, Kaley. And great to see all the awesome work being done with SCISAT, and that's pretty incredible to get to 21 years for a 2-year mission design life. So congrats to everyone involved on that, and let's hope it keeps going. Okay, we're right on time. So we will move on to Jason, and Jason Zou will be presenting time series analyses of the ACE-FTS and MIPAS CFC-11 and CFC-12 data products. Go ahead, Jason.
Okay, let me see the screen. Okay, good. Okay, thank you very much. And I'm Jason, and research associate at the University of Toronto. So today I'm going to present the time series analysis for the ACE-FTS and MIPAS CFC-11, CFC-12 data product. Motivation and introduction. Why doing that? So one reason is ACE-FTS is currently the only satellite instrument measuring CFC profile in the atmosphere. And as you know, CFC, they are the major ozone depletion substance and banned by the Montreal Protocol in late 1980s. And this study is to evaluate the data quality of the ACE-FTS and understand how the measurement of samplings impact the time series. So to do this, we compare the ACE-FTS CFC time series with the European satellite MIPAS, and the time series was further decomposed into different modes. So then the comparisons just made between the modes, and this can make the comparison easy. So finally, we examined the ACE-FTS, the CFC data beyond the MIPAS period. Okay, here is a brief introduction for ACE-FTS and the MIPAS. So ACE, and Kaley has introduced that before. Maybe I can just skip that part. But the key points is ACE-FTS is using solar occultation measurement. So it has 2 measurements per orbit, and on the other side, the MIPAS measures the vertical profile through the scanning the limb emission. Therefore, it has a much larger data sampling density. And MIPAS, they have 2 phases. One is a full resolution phase, and in the first 2 years, and then followed some failure. It goes to the reduced resolution phase. So we use the reduced resolution phase from 2005 to 2012 to compare with the ACE-FTS, because this is the only time they have overlapping. And MIPAS, they have 74 profile measurement during full resolution phase, and then 98 during reduced resolution. So it has 10 times larger, no, 50 times larger coverage than the ACE-FTS. So we make the ACE-FTS zonally average the monthly mean profile over several latitude bands. The bands will build a 20-degree latitude interval and this plot shows the FTS data points at 20 kilometer, and the axis is the time, and y is the latitude. So they are yellow lines. They are the yellow lines. They are the boundaries of the latitude bands. And for each latitude band, we build 4 type of time series, ACE-FTS and the MIPAS coincident data time series. And then we also build a time series from the all ACE-FTS samples and from all the MIPAS samples. So after this time series were built, we make the multilinear regression analysis. So the components contain the linear components, annual cycle, QBO, and semi-annual cycle. So from the right plot, you can see that at a higher latitude, ACE-FTS sample only 2 seasons per year, so you cannot use in the semi-annual component. So as a background, so this slide shows the zonal mean distribution of CFC-11 and CFC-12 averaged from 2005 to 2012. Left is 11 and the right is 12. The basic structure is either you have a higher concentration in the troposphere and then decrease with altitude. And between them, CFC-11, we cannot go higher than they are not going to higher than the CFC-12. So the structure is because the emission is from the ground, and when they go to the atmosphere, either through the broad Dobson circulation, they have such a altitude and latitude structure. Sorry, sorry. Okay. So this slide shows the constant components extracted from the constant component extracted from the 4 time series over the 9 latitude band. So each color is from different time series. You can see they are almost identical. It means that the different samplings didn't change this component. And the basic structure is you have a higher VMR in the troposphere and then decrease with altitude and follow the broad Dobson circulation pattern. Next slide. Okay, so this slide shows the linear trend component. In the lower part, we see the negative values in the troposphere. They have a slightly negative value, but in the stratosphere, in the southern part, they have a positive trend. So over this time period, and on the other side, they have the negative trend in the northern hemisphere. So why it happens? So because it's kind of not what expected. So this is the one explanation is offered by our colleague, Dr. Stiller. The reason is that there is a meridional shift of broad Dobson circulation between period 1 is 2005 to 2008, and the second period 2009 to 2012. The left plot shows the CFC-12 difference between the period 2 to period 1. You see the positive anomaly in the southern hemisphere and the negative anomaly in the northern hemisphere. The reason could be there is a shift of broad Dobson circulation from the southward. So the middle plot is the is from the paper of Gabi. It shows the angle 2 difference for the same time for the same period. So you see the middle part is very similar to the left part. So the right column shows the sensitivity study. using a model, what happens if there's a shift of the subtropical transport barrier. So basically, they have the general similar structure. This supported the hypothesis of the Dr. Stiller that there is a barrier in the shift of rhodopsin circulation. So this slide shows the QBO components extracted from the ACE-FTS in the top panel and the MIPAS from the bottom panel. So the left is from the southern hemisphere, middle one is equator, and the right is north hemisphere. You see the very similar between the ACE-FTS and the MIPAS, and they are out of phase between the southern hemisphere and the equator. This one shows the annual cycle pattern. Again, the top plot shows the ACE-FTS and the bottom is MIPAS. So we see the subsidence due to the broad observation. And in the equator, they're looking like standing waves. Again, my ACE-FTS agree very well with the MIPAS. Okay, finally, let's talking about the entire ACE-FTS. So this plot shows the mean CFC-12 and CFC-11 averaged over the tropical area from 60 south to 60 north, 5 to 10 kilometers. The left is the CFC-12. You can see the constant decreasing of the CFC-12. And the right plot is what happens for the CFC-11. And the red curves, they are the polynomial fit. And here there are some breaking point. The first one and the second one, they are estimated from the second order of derivative of the polynomial fit. The first one occurred after 2012, which was found where in the eastern part of China, and there are some small factories producing insulation material or refrigerator. Then some CFC-11 was released. And the second breakpoint occurs about 2018 after the intervention from scientists and the international community and the Chinese Ministry of Environment. And after this intervention, so these factories stopped producing the CFC-11. So this slide shows again the 20 years evolution of CFC-12 in the troposphere. So at altitude 9 kilometers. So the left is CFC-12, the right is CFC-11. You can see the general feature is decreasing. So, but for the CFC-11 around 2012, it's very hard. There is some sudden changes. So you have to average a big area to remove the noises. So this plot shows the similar plot, but for the stratosphere at altitude of 27 kilometers. And the right is from CFC-11. So for such an altitude, you can only see some signals at a lower latitude. And for the CFC-12, you can see a lot of features. You can see some QBO patterns. And here, these positive are because of the change, shift of broad optic circulation, and there are some southward migration. And finally, we have conclusion. So I have 1 minute left. So the thing is, a major point is the alternating positive and the negative trend seen in the southern hemisphere and the northern hemisphere during the 2005 and 2012 explained the Validation shift. They should not be confused with the overall decades-long CFC trends and exceptional features that appeared due to unregulated CFC-11 emissions and the cessation of these. So on the ACE-FTS provided this unique long-term data set of CFC-11 and the CFC profiles containing information spanning over 2 decades for monitoring the evolution of ozone depletion substance relevant to the MAESTRO project. So that's it. Thank you.
Thanks very much, Jason. Really interesting stuff. But I guess I say that not only because I'm a co-author, but it's really cool to see all that can be done with the ACE-FTS results.
Yeah, it's very, very rich data set. Yeah.
Mm-hmm. Any questions from people?
Nothing yet on event Moby, Kaley. And I know we are right at 1:15. So maybe we should move on to Doug's presentation. I see Tom is in the Zoom. Tom, if you can hear us, the technical hosts have requested to change you from attendee status to panelist. There is a pop-up you need to accept. So hopefully you see that pop up on your screen and can join as a panelist, and then we'll be able to fit you in after Doug. Okay, on that note, we'll hand it over to Doug Degenstein, and this is on OSIRIS, another year of data. So take it away, Doug.
Okay. Thank you. I'm just trying to sort out my screen here. There, that's going to work a little bit better, hopefully. Can everybody hear me?
Loud and clear, and we see your slides full screen.
And you see my slides perfectly. For those of you who have attended this conference for the last few years, I've welcomed you to my basement, to my office, and now I'm going to welcome you to a hotel in the Netherlands. Kaley and I are at an Altius Mag meeting. Kaley is doing a marvelous job of chairing, given that she just got off an airplane this afternoon. So what you see here is basically the sky as seen by OSIRIS. The OSIRIS instrument has been for the last 24 years or thereabouts, flying in the plane of this picture, in the plane of your screen, measuring through the blue sky and measuring the scattered sunlight, which is basically at 90 degrees from the lines of sight that come from the spacecraft. And we have been measuring ozone absorption, NO2 absorption, scattering of sulfate aerosol, and scattering of neutral particles. I'm going to tell you all about that. But I also want to tell you about the people there. Daniel Zawada, Landon Rieger, Kimberly Dubé, those names you see there. I'm going to feature their work as we go through this. So, very quickly, I'm going to give you a bit of an introduction, then I'm going to tell you about limb-scattered sunlight. I'm going to give you an update on what OSIRIS is doing today, and then some recent science, and like I said, from Kim, NO2 and NOx trends. Daniel and Kim are doing stratospheric temperature, and Landon is doing stratospheric aerosols. So temperature, aerosols, and radiative transfer modeling is sort of going to be the focus of this talk. Odin and OSIRIS. I think many of you have seen this before, but Odin is a 1 meter cube spacecraft, and it's got 2 instruments, a submillimeter radiometer and the OSIRIS instrument that you see there on the bench. It was launched in February of 2021 into a sun-synchronous near terminator orbit. I just got to get rid of something here on my screen that's driving me crazy. Okay, good. And we have been operating since basically October of 2021 at a 600 kilometer altitude orbit. OSIRIS, and I'm only going to talk about the OS part, the optical spectrograph part, single line of sight measures, single line of sight along the satellite track. We've got a grading spectrometer. We measure from 280 to 810 nanometers with about 1 nanometer resolution. And Odin scans rotates itself to take the single line of sight and make vertical tangent altitude profiles. And the spectra that you see over here in the upper right-hand corner, those are individual measurements. The black, the red, the green, those are individual spectra. And what you see on the left here is our basic grid, wavelength, and tangent altitude. And that's sort of our measurement set that we retrieve NO2, ozone, sulfate aerosol, and temperature from. Limb scattered sunlight. So I think most of you have probably seen this picture before, so I'm not going to talk much about it, but we measure limb scattered sunlight and we need a radiative transfer model to simulate that. And the radiative transfer model that we have developed, we call SASTRAN. The key to this slide here is that OSIRIS measures a lot of data and we don't use much of it at this point in time. You've got this tangent altitude and wavelength grid, and really we only use small regions of this two-dimensional grid. For instance, over here where the cursor is, we use this region in here to measure ozone, wavelength and tangent altitude. We have been developing the SASTRAN model to take into account all of the other species outside of ozone, NO2, and temperature and aerosol, like water and oxygen, and BRO and SO2 and O2, the O4 dimer. And this is a bit of a sales pitch now. We have a new version of the SASTRAN radiative transfer model, and now it was originally developed for limb scatter, but we have been using this now for tempo retrievals, for OMS-LP retrievals, for Altius retrievals, for mesospheric photochemistry retrievals from the Swedish MATS instrument, for nadir-looking thermal emission and limb thermal emission, and the IFTS that is prototyped to fly as part of AOM that measures reflected sunlight off the ground. SASTRAN has been used for all of those things. And I'm leaving this slide up here because if you need a radiative transfer model, Google SASTRAN2 and go to the SASTRAN2 website, well documented. And it comes with a good user support guide called Dan Zawada, who developed the whole thing. In the beginning, SASTRAN didn't, and what you see here, in the beginning, 20-some years ago, we were unable to model these photochemical absorption features in the spectrum and a lot of other things. This is a picture from a paper from some 20 years ago. This is the latest where we've now included NO2, BRO, SO2, water, and all sorts of other things. You see now we can actually model the A-band and the water absorption. Very early stages for this SASTRAN2, but everything is looking very good. The key thing about SASTRAN2, it's computationally way more efficient than the previous versions as well. So very quickly, OSIRIS today are measurement statistics. So you've got time series and latitude, and these are scans per month in 5-degree latitude bins. We don't measure in the polar winters, so that's why there's white there. And the key thing about this slide, and I've shown similar versions of this before, but probably the key thing is that bottom right-hand panel. The sampling as far as latitudinal coverage has gotten better. We have an instrument issue where our power supply overheats and we have to turn the instrument off. We're getting better at managing that. The data quality has not decreased, but the amount of data, the duty cycle has gone down, but we've got it tuned so we still cover the globe. The temperature has been varying as a function of time and then stabilized. I don't think I'll go into that in too much detail, but what it has caused, it's caused a bit of a pointing bias. We have star trackers that are not thermally connected, so to speak, to OSIRIS. The spacecraft between the star trackers and OSIRIS may torque with different temperatures and twist. And we have a pointing offset. We get the pointing from the star trackers, and there's a bias that has to be corrected, but we can do that by looking at the atmospheric limb and looking at the signals. And we have been doing this now for the 24 years. And this is the curve of the bias offset. And what's happened is it got worse, 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 worse. Then it got better in 2021, and it seems to have stabilized in the last couple of years. So why? We're not sure, but our orbit drifts and our thermal profile changes. So that's probably it. Level 2 processing updates. We've just recently released a version 7.3. It's ozone, it's stratospheric aerosol, it's NO2, and a brand new stratospheric temperature product that I'm going to tell you a little bit more about here in a bit. We include all of the pointing corrections. We have become much more automated with our data. It took us 20 some years, but we're much more automated in a way that we can actually get the data products to end users quicker. And one of the things, one of the reasons for that is we now use MERA2 instead of ECMWF. It's just easier to get. Recent science. So I've always talked to you about ozone when I've talked to you about recent science, but I'm not going to today. We've done all sorts of good ozone stuff, but I'm going to highlight a few other things. Usually I talk a lot about nitrogen dioxide, NO2 as well, and this is the work done by Kimberly Dubé. I'm just going to show one picture here. OSIRIS and SAGE-2 NOx products. Photochemical model is used with the OSIRIS NO2 to get NOx, and we're showing a NOx increase from 1984 to 2021, because if we've merged the two data records, we have this data set that goes back to 1984. And the key thing is, and if you want more details, contact Kimberly. The rate of NOx increase in the tropics is greater than can be explained solely by N2O emissions. So Kimberly's been doing a lot of work on this. It's ongoing. And if you want more information, you should contact her. Upper stratospheric temperature. This is a new product. Dan Zawada did the retrieval, and Kimberly and Adam Barassa have been looking at this. We measure temperature in the upper stratosphere by measuring the neutral density N2 and O2 and using hydrostatic equation, etc. The details you can ask Dan Zawada if you want more information. But the key thing here is we have compared and we have biases with respect to ACE-FTS, which are less than 3 degrees Kelvin, and biases with MLS. Below 55 kilometers, less than 5 degrees. And we believe this is a good product for people to start to use. We have merged it with the SSU and AMSUA data records that have been ongoing for many, many years. We've got a data record now from 1980 all the way to 2020. There are biases, but these biases, when removed, seem to give good trend results. And here are some trend results for these merged data records. SSU has also been merged with MLS and with AMSUSU, and these are the comparisons, and basically the trends that we get in degrees Kelvin per decade at different latitudes agree to within the regression uncertainties. And I'll skip over this one. This is basically the profiles, and OSIRIS, SABRE, and MLS show good agreement, except for MLS does some goofy stuff. Stratospheric aerosols. I just want to touch on this quickly because this is Landon Rieger's work, and it's one of the things we've been extremely interested in with OSIRIS for over 20 years. We make data records that are used in climate modeling as part of the GLOSAC climatology. We have merged these with the OMPS LP aerosols from our USASC product. We've merged with SAGE-3 ISS and all the other SAGEs. And this is a time series, and what you should take from this is up until just before 2020, all of these instruments seem to give consistent results. And then Hunga Tonga happened. And this has given us a lot of good things to work on, especially in light of the fact we have our ALE instrument is manifested to fly at the latter part of this decade, early part of next decade on the HawkSat, which is part of the Atmospheric Observing System, which is NASA's decadal survey system for measuring clouds and aerosols. The thing is, after Hunga Tonga, the particle sizes in for the sulfate aerosols in the atmosphere changed dramatically. All of these instruments, except for SAGE, rely on particle size and a knowledge of it, and the a priori knowledge made things messy, which gives us good work to do, which is really good. The next couple of slides are showing that OSIRIS and SAGE, when compared with each other at these coincident points, really were bad comparisons in 2022 and 2023, but pre-eruption they were good. We needed to find a particle size. So there are two parameters, the log normal width and the log normal mean radius. We decided we could use the SAGE-3 ISS measurements to come up with these particle sizes. That's what this says. Landon implemented a Rogers-style inversion and came up with some particle sizes. And lo and behold, pre-eruption, we're still good. During the eruption, Hunga Tonga eruption were much, much, much better. But after 2022, things aren't quite so good. And Landon gave me another picture to show, and I'm not going to show it. So it's a work in progress. Landon is doing a very good job on this. If you're interested, talk to him. I think I'm pretty well out of my 15 minutes here. I conclude. Everything looks good. Even after over 23 years of age, we are still producing high impact science. So thank you for your attention.
Thanks very much, Doug. Just a titch over time, but yes, I agree. The Hunga Tonga stuff was definitely worth showing because that's really cool. So I'm going to encourage people to take comments and questions offline. Maybe we can do them through the event Mobi, and we can relay them to you, or we can put people in touch with you. Okay, we now have Tom McElroy. Can you share your screen, please? Let's hope.
Can you hear me?
Yep, we can hear you.
Okay, good. And what do I have to do to show my screen?
Do you want me just to show your slides and then you can tell me when to flip them?
That would be good. Yeah, that would work.
If I can do that, then that.
We'll just get on with it.
Well, we want the easiest, straightforward way. Okay, is that visible for everyone?
Yep.
Okay,
The
so
picture here is my poor little instrument, which occupies about a half a meter cube, sitting on the 30,000-pound shaker in David, Florida, where they were trying to break it. Next slide. Okay, I'm going to talk a little bit about MAESTRO, the instrument, the measurement problem, a couple of results, and some interesting things about what's been happening while the instrument, along with its owner, has been getting older. The next slide, please. Okay, these are some pictures of the engineering model that sits in my living room. You can see some of the interesting features about the instrument. One is that the field lenses that produce the image that goes onto the entrance slit on the far right are mounted right on the spectrometer, so we have that stability. On the left side, far left side, you can see that the two gratings of the instrument are mounted on a flexure pivot that allows us to actually do microscopic changes in the position of the spectrum to look at subpixel variations. And it includes an important little bit of ABS plastic that compensates for the expansion of the aluminum frame relative to the expansion of the grating, which is much slower, of course, because they're made of glass. And so the spectrum is compensated with temperature so that the line shape stays constant even if the temperature of the instrument changes. The other information you can read on the slide. Next slide, yes. Since the last time I did a little talk like this in Newfoundland, we've added a refraction code to extend the MAESTRO tangent altitudes below the levels where FTS is retrieving them in the lower atmosphere. Sometimes FTS doesn't give altitudes below about 12 or so kilometers, and MAESTRO continues to measure below that. I had a hard-coded lower limit of slant column amount that I put in when I was developing the codes 20 years ago, and I found out that that turned out to be a problem, limiting the performance at higher altitude and causing some really strange things that go on above 40 kilometers or so in altitude. And then while having fixed that, I found out that our signal to noise is really falling off rather too much, above 40 to 50 kilometers. And so I'm using a curve fitting process above those altitudes to stabilize the inversion at higher altitudes. And I do a little push for Jeff. He'll be talking about some of the more recent reprocessing all of the data in another talk. Next slide, please. The problem in doing an occultation measurement is this huge change in intensity as a function of both altitude and wavelength. As you can see in the plot, this is MODTRAN data that I used to actually calculate the observing tables for the instrument that we're still using on orbit. And it is quite a dramatic change if you notice that it's a logarithmic scale on the left side. Next slide, please. In order to adapt to that, I basically used changes in integration time, the number of pixels being observed in one observation, and the number of coads that would be done in order to optimize the signal to noise ratio. So each one of these observations that you see in this plot have been done with a different set of parameters in order to optimize the signal to noise. And one of my colleagues at Johns Hopkins atmospheric physics group actually said, it will never work. It's too complicated. But it did work. You can see that in the plot. I've normalized the two scales so the blue and the red agree in the reference spectrum at the top, and you can see that all the other ones are linearly compatible on both sides. Next slide, please. And using the reference spectrum, we can convert the measurements into optical depth, which you see here. You can see the absorption from ozone in the Chapuis band clearly coming into visibility there in the red curves. Next slide, please. This is a retrieval using the retrieval algorithm, which is a Tomy-Tikhonov retrieval. And you can see at about 50 kilometers there's a sort of a jump change there. I'm still working on how to fit together the curve fitting part above that altitude with the raw data lower down. Next slide, please. And we're also retrieving water, as you can see on the left, and NO2 on the right. Next slide, please. And the interesting part that's kind of really new stuff for this particular meeting compared to the others is the question of how is the instrument doing as it gets older. The interesting part is that some kind of contamination on the main mirror that points at the sun and brings the light into both instruments has actually resulted in a severe decline in sensitivity at shorter wavelengths. It doesn't really show too badly in the 2873, which was not too long after launch. We launched in August. This was a measurement in the following year in February. And the visible is on the right. the UV on the left. Next slide, please. And what happened, of course, is that contamination by the time we reached, 2021 had practically wiped out the UV altogether. It affected the visible at the short end as well, around 500 nanometers. Next slide, please. And if we actually do a direct comparison, the one on the left is the one I showed you before from 2004. The one on the right is expanded by a factor of 10, so it's about 60 times dimmer than what you saw in the plot on the left, and it has a particular spectral behavior as well. And it meant that we couldn't do the NO2 at all after that, beyond about 2008. Next slide, please. And of course, it worked really bad damage for the ozone retrieval, as you can see, with the UV retrieval in the blue compared to the retrieval in the red. The purple one is the retrieval produced by the FTS instrument in the infrared. I'll make another comment about that comparison a bit later. Next slide, please. And we really see a big difference here, between the one on the left and the one on the right. As I said before, it's really very small compared to before, but it has returned quite a lot. It's about a sixth of the original value, but because the signal to noise changes with the square root, we can still get a measurement in the 450 nanometer region where NO2, the NO2 structure is available to make a measurement. Next slide, please. And so there we have a measurement of NO2 on the left and the ozone on the right. Could I have the next slide, please? And we're also seeing reasonable aerosol. I'm really not quite sure whether we believe that blue curve or not. Certainly when you get to those very short wavelengths, the 527, we can be looking at very small particles, which would deviate quite a lot from the wavelength dependence of the other wavelengths. Next slide, please. Okay, so what we're doing now, we want to validate the new version that I've just described with a sample of data, and then implement it and reprocess the data set and take a look at the whole data set together. And I have a discrepancy between the MAESTRO altitudes and the tangent altitudes. And I believe it's because the assumption on the FTS side is that a bilateral or a double-sided interferogram will average out a linear change with time. But in fact, when we in the atmosphere, we're seeing changes that change with the density, which means they change with a logarithmic term. And I think I'm going to have to do some serious modeling to understand how to relate the MAESTRO tangent heights with the FTS in order to do the best job down below 10 kilometers where the density changes are really important. One of the general comments I'd like to make, though, is this is one of the few times that two instruments making tangent altitude measurements, occultation measurements, have actually been flown where they're looking down the same optical path. And the incredible agreement between the FTS and the MAESTRO data are a really important and interesting conclusion, even though it appears to be telling you nothing. What it's telling you is that the particular wavelength correction I use as a function of temperature on my side and the data from FTS, which is obviously temperature corrected already, actually are agreeing very well. And that means not only is the spectroscopy on both sides doing a good job, the retrievals are handling the temperature problem as well. The next slide, please. And there we are, 2003, just before MAESTRO got put on that rocket and shot into space. Thank you very much for your attention.
Thanks very much, Tom. It's great that we were able to connect with you and get you on. Alec, do we have any questions for Tom in the chat or the Q&A?
Nothing there yet, but if anyone has any questions for Tom or any of other presenters, we have a couple minutes left until the end of the session time and the break at 1:50 Eastern. So feel free to write your questions in the chat if you have any, either the chat or the Q&A. And I'll keep monitoring.
Maybe I'll throw the question to Tom and then to Doug. It's been more than 20 years since we put ACE, MAESTRO and FTS and OSIRIS into space. Can you tell us what we've learned and what we should be doing now? I throw it to Tom and then I'll throw it to Doug.
Well, one thing I learned was that you have to have a very clean environment on your spacecraft if you're going to measure in the UV. I've actually been exchanging emails with John Burroughs just in the last week or so because the same problems have occurred on Skiyamaki and on GOM-2. And so it's really important that the scientists have enough influence to make sure that the people building the hardware really build it properly. I think scientists had a lot more influence with GOM-1 than they did with later satellites. And I think it's probably also true in the case of OSIRIS, but of course, Doug can comment on that.
So, okay, I was going to come at that from a little bit different angle, but your answer is not that far different from mine. We back 20 years ago, we had scientists 25 years ago, etc. The scientists worked very, very closely with the industrial partners. We didn't have a complicated procurement process from the government, and we were able to, for not that many dollars, put things into space. Things have got way too complicated. The risk tolerance, the risk acceptance for major projects has gone way, way down. We need to get back to those days where scientists and industry work together to produce good instruments to do good science. So I think that's kind of, that is where you ended up, is it not, Tom?
Pretty much so.
Yeah.
I could say a little bit more than that in two areas. One is that I'm probably the last man standing that actually built the instrument in my own lab and actually, you know, set it up and calibrated it and focused it and so on with my own hand, right? And at the same time, we had this problem. We told the industry multiple times that they had to really make the plate that the instruments were mounted on very clean, and they needed to never put blind tapped holes in because it traps chemicals, right? That you have to have it clean. And when the duplicate plate arrived at U of T, we actually took a hand drill and drilled out all the holes because we never would have been able to pump it down in the vacuum tube or in the vacuum chamber in time to make the measurements we needed to make. And it took 18 years on orbit for that stuff to disappear.
Yeah. Yeah, we only had 45 days to test in that tank, so it would have taken for much longer than we actually had been budgeted. Doug?
No, I don't have too much more to add. I agree with Tom. Let's go. Let's leave it at that.
Okay. Alec, do we have anything else in the chat?
I don't see anything else in the chat on my end or in the Q&A panel. But we've got 2 minutes left if anyone has anything pressing they want to share. In the meantime, I want to thank all of our presenters from this first part of the SCO Satellite Earth Observation session. It's been a great first set of talks. and remind everyone listening that starting again in just over 15 minutes time, we have part 2 of this session, followed by part 3 later today, and we have part 4 tomorrow. So lots more great talks coming up. And a new question just came in. A practical presentation. Yeah, that's more of a technical question. But yes, a practical question for the chairs presenting in the next session. Can I share my screen? How? Or will you control the slides? You can share the screen from your own end. Presenters, please make sure you go through your email. Kaley has resent the link for the Zoom room. We are in Zoom D if you're a presenter for all of the satellite Earth observation sessions. Once you are in the Zoom meeting, you'll be converted from an attendee to a panelist by the Advanced Systems host, our technical support, and then you will have the rights to share your screen within Zoom. So presenters will be able to share from their own end if they desire. And yeah, and on that note, anyone presenting in the next session, please join the Zoom.
And thank you very much, everyone. It's been a great start, and I look forward to hearing more about aerosols and clouds and radiation when we come back. And thanks to the 4 of you.
I'm going for dinner, Kaley. You gonna join me?
I need to know.
Oh, I feel sorry for you.